Just waiting for them. Okay, sir. So we are live on YouTube. So we will start this session now. So first of all, I welcome all our participants, the 550, more than 550 participants from all over India to this live session, which is being delivered by Professor Arun Bisham. So Professor Arun Bisham, he is let me just introduce you to our speaker, Professor Arun Kumar Bisham. So he's professor at Faculty of Natural Sciences, Mangosuthu University of Technology, South Africa. Professor Arun Kumar Bisham, he retired at the end of July 2018 as senior professor in the Department of Mathematical Sciences, Faculty of Science and Agriculture at the University of Zululand. Currently, Professor Bisham is serving as a research professor at Faculty of Natural Sciences, Mangosuthu University of Technology, South Africa, and School of Mathematical Sciences, University of KwaZulu-Natal, South Africa. He's also a visiting research professor at GLA University, Mathura, India. Professor Arun Kumar Bisham obtained his PhD degree in 1988 in applied mathematics through University of Cape Town. He has given over 200 invited talks in all over the globe and have published around 200 research papers. He is currently rated C2 by the NRF and has refereed articles for several prestigious international journals. Several students have completed their master's and doctoral degrees under his supervision. Professor Bisham is also guiding some postdoctoral fellows. Professor Bisham has received several awards like CSIR Doctoral Bursary in 1985, then University of Zululand Council and Senate Research Grant in 1992. He also got Council Travel Grant in 1995, then the Council Research Grant in 1999 for various research projects overseas. He has also served on the panel of the NRF that deals with the allocation of research grants in the mathematical sciences, as well as the panel for allocation of master's bursaries. His area of research interest are general relativity, cosmology, relativistic astrophysics. Professor Arun Kumar Bisham will be delivering the lecture on Introduction to Dark Energy. So I will hand over this session now to Professor Arun Kumar Bisham. Please, sir.
Thank you very much, Dr. Singh, for that introduction. Let me start sharing my screen. Okay, now. Okay, can you see my screen?
Yes, sir, we can see, sir.
Okay, I would like to begin by thanking the organizers of this conference on applicable mathematics, the refresher course on applicable mathematics. It is indeed a great pleasure for me to be able to deliver this lecture. So today I will talk about the nature of dark energy, which is a very important problem in cosmology. In fact, it is one of the most important problems in cosmology today. So I am affiliated to two universities at the moment, the University of Zululand as a research fellow and as a research professor at Mangosuthu University of Technology. I just want to begin by showing a few pictures of these two institutions. So first of all, this is an outline of my talk, introduction, early history, revolutions in cosmology, something about inflation. Then we come to the main topic of this talk, which is dark energy. Sorry, I don't know why this introduction appears twice. Then something about dark matter, the future of the universe, and then finally a conclusion. So here are some pictures of the two universities. First of all, here's a map of South Africa. We have 9 provinces or states, which are shown here in different colors. Sorry, this map is a little bit outdated, so some of the names of these 4 provinces here have now changed. And there's a landlocked country called Lesotho, which is situated here. So I live in this city called Durban, which I think most of you have heard about. And the majority of Indians in South Africa, remember we came way back in the 1860s and so forth to South Africa, and most of them have settled in this area here of KwaZulu-Natal. Now, the University of Zululand is situated somewhere over here to the north of Durban, and Mangosuthu University of Technology is actually situated in Durban itself. So here's a picture of the University of Zululand. This here is our main administration building. In the distance, you can see our library. And some other buildings here. As you can see, it is situated in a very rural setting. Here is another picture of the university, the main administration building again, and then two pictures of our library. And here's a little picture from the distance of the university. Then here is a picture of Mangosuthu University of Technology. This is the sort of main road from which one enters. This is the main entrance. This here is the main administration building. And this quadrangle here has most of the lecture theaters. Here are some student residences on this side and so forth. There's some very nice grounds here. There's a ground here where they play mostly soccer. And then another picture of the university taken from the other side, showing again the many buildings. And then again, another picture showing the main administration building. Right, so now I'll get into my talk proper. If you look out towards the sky at night, what do you see? You see a picture, something like this, with various stars in the sky. This picture is taken from the southern hemisphere, and what you see here is a group of stars, a group of 4 stars, which is called the Southern Cross. And there's another 2 stars here. So in the past, many of these sort of patterns of stars were given various names, and that was used to identify them in the sky. So the question that arises is, we see all these stars in the sky. What are they made of? What will happen in future? How did the universe start? So stars rarely occur by themselves, but they occur in groups. And a group of stars is called a galaxy. Now, a galaxy has about 10 to the power 11 stars. Now, what is 10 to the power 11? 10 to the power 11 is 1,000 billion, where 1 billion is 10 to the power 9. So I hope I don't make this talk too simple for some of you, but I thought that since we have a very wide background of people present, I have tried to keep it simple so that most people can get some understanding of cosmology and dark energy. Right, so a galaxy has about 10 to the power 11 stars, and there are about 10 to the power 11 galaxies in the universe. Now, when I say in the universe, what I mean is what we can see, what we can detect. Because really, we don't know what's outside what we can detect. And I will say more about that a little later on. Now, apart from these stars, which are grouped into galaxies, there is also some matter which is in between the galaxies or stars, and this is called interstellar matter. But this forms a small percentage or proportion of the matter which is in the stars and galaxies. So how many stars do we have in total? If you add these two up, you would come to a figure of about 10 to the power 22 stars in the universe that we can see. And this is a huge number. So the question that we can ask is whether the universe is just made up of all these galaxies and stars, or is it? Is there some other type of matter that we cannot see with our optical telescopes and so forth? Now, we will try to answer these questions as we go along in this talk. So what is cosmology? Well, cosmology is a study of the large-scale structure and evolution of the universe on the scale of stars or galaxies. In other words, what is the universe made of? How did it start? How are the elements formed? How are stars formed? What will happen in future? How will the stars or the galaxies end up? Right, so we mentioned that most of the stars are grouped into galaxies. So what does a galaxy look like? Well, this is a picture of our own galaxy, which is called the Milky Way. Now, you can think of a galaxy as a sort of saucer-shaped structure, and this is the sort of main part of the saucer that you can see. Here, one is seeing it edge on. So you see this sort of band here where you see most of the stars and all the matter, and then you see some stars outside that. So if you look at this from this direction, that is, if you look at it from the top, what do you see? You see a picture something like this. You see a sort of central core here, and then outside what you see are some arms, right? So this, the sort of spiral structure leads to the name of a spiral galaxy. And this is a diagram of our own galaxy. Now, what about other galaxies? What shapes do they have? Now, you have a very wide variety of shapes. You have the very spherical ones, and they are classified into various categories. These spherical and elliptical galaxies start from E0 to E7, with E7 being the most elliptical. And then you've got these spirals here, which are broadly divided into two groups. On this side, you have the sort of ordinary spirals here. And then here, what you have are called the barred spirals. Now, why they are called barred is that if you look at the center, the core of these galaxies, you will see that there is a bar-shaped structure here, like a sort of dumbbell. And these are not the only types of galaxies that you can see. You can basically see galaxies with sort of more or less any type of shape, like and these are called irregular galaxies. Although most of the galaxies that we can see will be of this type here. Right. So how do we study the universe? Well, we can apply Newtonian theory, but Newtonian theory was found to have many problems. One of the main one being that in Newtonian theory, if you send a signal, then that signal travels at infinite speed. If you send some electromagnetic signal, like if you shine a torch, assuming, of course, that the light of the torch is wide enough to reach the end of the universe, then that will travel immediately to the end of the universe. Now, we know that this is not correct because nothing can travel faster than light. So that sets a maximum speed for any type of communication to take place. And what we need to do is we need a better theory from Newtonian theory. And in 1915, Albert Einstein came up with this theory, which is called general relativity. And in 1917, excuse me, he applied it to cosmology. Now, we must remember that at that time, the universe was thought to be static. In other words, if you look at the stars in the sky, they seem to be in the same position. Of course, taking into account that we are rotating about our axis, and that also our galaxy, let me just go back to this diagram. Our galaxy is also rotating at a slow rate. Sorry, just to show you where we are situated, our galaxy is situated, our solar system, I should say, it's situated about 2/3 from here to the end. So it would roughly be about here, right? So say somewhere here or here in this diagram, yeah. So at that time, the universe was believed to be static. So in other words, the stars were essentially in the same positions, the galaxies, and there wasn't any sort of uh, 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 movement of the galaxies. So it was very natural to look for a static model, a model that which did not change with time. However, when Albert Einstein formulated his theory of general relativity, these were the equations of the theory. Basically, you can think of these as, they are tensor equations, but you can think of them as matrix equations. Each of these indices can take values from 1 to 4. So in total, you've got 16 equations, but because these are symmetric, you end up with a total of 10 equations here. Right, so when he was looking for a static model, he found to his surprise that his equations did not actually admit a static model. So what he did was he introduced a constant into his equations, which is called the cosmological constant, this lambda here, because the mathematical structure of his theory allowed for the introduction of this term. So these equations here are the most general form of the equations of general relativity. Now, once he did this, then he was able to obtain a static model, which is called the Einstein static model. Right, here's a picture of Einstein, who is considered one of the greatest scientists of the 20th century. This photograph was taken in 1905, and during that year, he published 5 monumental papers, all in 1 year, while he was still working as a patent clerk in Zurich. Sorry, I think it was in Bern, yes. And each of these papers was very monumental, and probably each of them could have earned him a Nobel Prize. He did actually receive the Nobel Prize, but that was a little bit later on, because initially people didn't actually accept the theory of general relativity. That only came later on. And then here's another picture of him. Here he is here, which he's delivering a lecture in Paris. This was around 1922. Right, so coming back to the Einstein static universe, it is what one may call closed. In other words, the universe, okay, I'll come to what this means a little later on. And it is finite. So it's not infinite, but finite. Right, so just to get a few parameters or quantities of these models, we will let A be the scale factor or the radius of the universe. And in general relativity, we don't actually deal with Euclidean space only, but one can have curved spaces. And this quantity K denotes the curvature of the space. If K is 0, then we have Euclidean space. If K is positive, then we have positive curvature. And if K is negative, then we have negative curvature of your space. So in the static model, since it's static, your radius is constant, and K is equal to +1, corresponding to a closed model. Right, so as soon as he came up with the static model, then there were several interesting developments which took place. In 1917, a scientist by the name of Willem de Sitter found an empty, there was no matter in the universe, but it was expanding. It was a solution of Einstein's equations. So the empty or the vacuum solutions are also very interesting because they give us information about the actual universe. And this solution had a non-zero value of lambda, but what was interesting was that it was empty. So in this model, the cosmological constant is a constant. Then the form of the scale factor or radius of the universe is an exponential function of time. And since it's empty, the density and the pressure of the universe is zero. And of course, K is also zero, so it essentially corresponds to a flat. K equal to zero also corresponds to a flat or Euclidean model. Now, this type of solution has come up several times in the development of cosmology, as we shall see later. Right. Now, what happened was that sort of from the 1910s to about the middle of the 1920s, an astronomer by the name of Slipher discovered what is known as a redshift of several galaxies. Now, what do we mean by redshift? If you take the light, if you take any light and pass it through a prism, then what the prism does is it breaks up the light into its various colors, and one sees various lines in what is called the spectrum of the light. So if one looks at the redshift of the galaxies and then compares the spectrum of the light with the spectrum of the light in the laboratory, one will see that the light of the galaxies is shifted towards the red end of the spectrum, and that is called the redshift of the galaxies. However, he didn't really give any interpretation to the redshift of these galaxies, and this came a little bit later. Also, in 1922, from the theoretical point of view, Friedman found non-static models without the cosmological constant. In other words, models that had motion in them. And he could be regarded as the first person to mathematically predict an expanding universe. However, this idea of an expanding universe was not taken very seriously at that time. And it was just thought to be some particular solution to Einstein's equations in cosmology. Then in 1927, another scientist by the name of Lemaitre also found some non-static models. And in general relativity and cosmology, there are many instances where certain important discoveries of the nature of the universe were actually missed. This is one of them because Friedman found these non-static models, Lemaitre as well, but they didn't associate it with an expanding universe. So this is an example of an opportunity which was missed. And in fact, even Einstein thought of Friedman's work just as a mathematical curiosity without any direct implications for the universe. So the idea of an expanding universe was not very popular or widely accepted at that time. Then the key discovery which came was in 1929, when an astronomer by the name of Edwin Hubble also discovered the redshift of many galaxies. And then it was him who associated or interpreted this redshift as a recession velocity. In other words, if the galaxy is moving away from you, then you would see the spectral lines shifted towards the red end of the spectrum. Now, just to show you a few pictures of the redshift of the spectrum of these galaxies, let's just first look at some units, because we're looking at galaxies which are very far away, and usually astronomers and scientists do not use meters very often because the numbers are so large. So what they use is what is called the light year, or another associated measure is the parsec or the megaparsec. So the speed of light, as we all know, is 3 times 10 to the 8 meters per second. Now, if you look at how far light travels in 1 year at this speed, that is called a light year. It's the distance light travels in 1 year, and it is given by 3 times 10 to the 8 times 60 seconds in 1 minute, times 60 minutes in 1 hour, times 24 hours in a day, times 365 days in a year. And that gives you this figure here of about 6 times 10 to the power 15 meters. So as you can see, it is a very large number, so it's more convenient to use light years. So let's look at some galaxies here, which which Edwin Hubble looked at. These are various galaxies. The Virgo cluster is known, Ursa Major also well known, and there are some other galaxies. This is the distance to these galaxies in light years, and you can see that even in light years, this is like 1,000,000 light years away from us. This one is about 4 million light years away from us. So if you take the light from these galaxies, you pass them through a spectrum, and you notice that certain lines are shifted towards the red end of the spectrum. So let's look at this sort of line here, which is called the H plus K line. You will see that the dot here is in this position for this particular galaxy. And if you, as you go further away, this dot shifts. This is the red end of the spectrum. It starts shifting towards the red end. I know it's not very clear, but the dot is here, and this arrow shows where it has moved to. In this diagram, again, further away, it's moved further to the right. There's the arrow showing where it is. This dot in this picture is somewhere over here, and there's the arrow which shows where it is. And finally, this one here, because it's the furthest away, has shifted the furthest here, and there is the arrow. And also, another discovery that was made by Hubble was that the further away a galaxy is, the faster it is moving away from us. This one is traveling at a speed of 1,200 kilometers per second. This one at 15,000, 22,000 kilometers per second, 39,000, and finally this one at 61,000. So galaxies are moving away from us at speeds which is proportional to their distance away from us. Now, does this mean that we are at the center of the universe and everything is expanding, moving away from us? No, it does not. Let's look at this diagram here. This is just an analogy to show you what is meant by the expansion of the universe. So you think of a balloon and think of dots on a balloon. Now, when you're using this analogy, do not think of anything that is either inside the balloon or outside. It's a two-dimensional analogy, so the whole universe is actually situated on the surface of the balloon. And what you see is that as the balloon is blown up, all dots are moving further away from each other, but you cannot say that one dot is at the center of the universe. So all galaxies, stars are moving away from each other with speeds which are proportional to the distance away from us. Now, if you trace this back in time, what you notice is that they're going to get closer and closer to each other. The galaxies will get closer and closer. And eventually, what will happen is that everything would get compressed. The pressure, the density, the temperatures, etc., will all tend to blow up. And finally, we have what is called the Big Bang. This is the Big Bang, and everything commenced from there. So that is why these models, or this model, is called the standard Big Bang model of the universe. Right. So after Hubble's discovery, most scientists accepted the idea of an expanding universe. By 1931, Einstein had also accepted it. And according to the recollections of Gamow, who was a mathematician essentially, Einstein had a conversation with him, and Einstein mentioned in that conversation that he regarded the introduction of the cosmological constant as the biggest mistake of his life. However, today, the cosmological constant is very important and is used to explain dark energy. Right now, another two scientists who were also involved in coming up with these first models of the universe were Robertson and Walker, and they also came up with these models. They cleared up some problems regarding to time and space that existed before that. So these models, the homogeneous and isotropic. By isotropic, we mean the same in every direction. And by homogeneous, what we mean is that if you take a certain volume anywhere in the universe, then the things like your pressure and so forth would be the same everywhere. And these Friedman, Lemaitre, Robertson, Walker models, that's why FLRW, are accepted as the best models for the universe. Right, now, historically, by the 1950s, this cosmological constant was rejected. At some stage, it was revived again, for example, to explain the age of the universe. But later on, it was found that there were some mistakes in the calculation of the age of the universe, so the cosmological constant was not needed. However, once one comes up with something like this, then it has important implications later on. Right. Now, one may think of three main revolutions in cosmology. The first one, which we already mentioned, was in 1929, that is the discovery of the expansion of the universe. Now, just to tell you how important this discovery was, recently, a couple of years ago, I think, there was a panel discussion about the greatest physics discoveries of the 20th century, organized by Oxford University. And here there were 4 Nobel laureates present. And the first 3 of them actually picked quantum mechanics or quantum theory as the most important discovery. But the 4th Nobel Prize winner, who is John Mather, actually picked the expansion of the universe. So that will tell you what an important discovery this was. Now, what was a picture of the universe at that time? Okay, let's just look at quickly the equations which describe these models. A here, which we already mentioned, is the scale factor or radius of the universe. K is your curvature constant, your cosmological constant, and then this is the density and this is the pressure of the universe. And the dots here denote derivatives with respect to time. And we mentioned that these equations were solved by Friedman. That was for the case when P is 0, which is a good approximation today because you don't find like galaxies colliding with each other very often. So the pressure is 0. And he solved it for the case K equal to +1. Now, in the early 70s, an astronomer by the name of Sandage, Alan Sandage, defined cosmology simply as a search for 2 numbers, which were h and q. The naught denotes the present values of these quantities. And he said that all of observational cosmology is just the search for these 2 numbers, your Hubble parameter and your deceleration parameter. Now, what are the definitions of these 2 quantities? The Hubble parameter relates to the expansion rate of the universe, which is A dot over A, and the deceleration parameter, Q, is a small correction to the expansion. As the matter slows down the expansion, it is given by Q is equal to minus essentially A double dot. Right, the others are just to make it dimensionless. And at that time, there was very strong belief that the expansion was slowing down. So a negative sign was put on here so that the value of Q would turn out to be positive. And so you have this relationship that if Q is greater than 0, it means that we have the expansion slowing down, that is the universe is decelerating. And if Q is less than 0, then that is associated with the acceleration of the universe. The universe, the expansion is actually increasing. And at that stage, it was just thought that one needed to determine whether the universe was, well, you needed to determine these two quantities here, that is your H and Q from observations. And then that would tell you also whether the universe was open, flat, or closed. Right, so let's look at a diagram of this, which will make it more clear. Here is a radius and here is a time. So the solutions to the Einstein equations are given here for the three different cases. This one here is a case when k is 0. This is when k is -1, and this is a case when k is +1. And this here denotes the present moment. So you see that the universe starts off here with sort of a very high expansion. And then what happens is gradually the expansion is decreasing in all of these models, right? So that was a picture of the universe at that time. Then came the second revolution, which was the introduction of what is called inflation. Now, what is this? We'll explain more what we mean by this just now, but basically it is a very fast or rapid expansion of the universe, which occurs very early on at around the Planck time, which is around 10 to the minus 33 seconds. And the initial person who came up with this idea was Alan Guth, who is a Russian relativist. And then in the 1980s, Alan Guth, together with two other Russians, Starobinsky and Lindy, they further developed the theory of inflation. And for this, they were awarded the Dirac Prize in 2002. There are many Nobel Prizes which have been awarded in relativity, cosmology, and related areas of astronomy. And they were also, well, two of them, that is Guth and Lindy, I'm not sure why Steinhardt was left out, were awarded the Breakthrough Prize in Fundamental Physics in 2012. Also, Starobinsky was left out. He should have been included here as well. And then this advent of inflation made more people interested in cosmology, especially the high energy physicists. And there were some problems which existed in the hot Big Bang model, and this theory of inflation solved some of these problems. So I won't go into the detail because of time, but these are the horizon flatness and monopole problems. And also, inflation provided a way in which one could generate some fluctuations in your density, which eventually led to structure formation, the formation of the elements, stars, and so forth, galaxies. Now, when does inflation occur? It occurs very early on, and it occurs from about 10 to the minus 36 seconds to about 10 to the minus 33 seconds after the Big Bang. And it was thought that around that time, the Big Bang model, together with inflation, described the universe to a first approximation. So here is a diagram showing inflation. Again, there's time here and the radius of the universe on this axis. And you see that in a very short time here, 10 to the minus 35 to about 10 to the minus 33, the universe expands roughly by about 60 orders of magnitude. Okay, don't worry about this because this diagram we showed earlier on. Right, and this is the present time here, if you look at your time axis here. Right, now, third revolution, which is one we want to discuss here, occurred in 1998 with, okay, there were two independent teams of astronomers who were looking at distant supernovae. Now, this is a type of star. I'll show some pictures of this just now. And when they looked at these, they're very far away. In fact, they're sort of roughly at the edges of the universe that we can detect at present. Now, what they found was, you see, the standard Big Bang model sort of give some idea of what should be the brightness of all these objects as you move further away. But what these groups found was that the brightness of these stars decreased faster than that predicted by the Big Bang model. Now, this initial dimming corresponds to an additional distance away from us, because if they are further away, then obviously they will appear more dimmer. And that, how can you explain this? Well, the only way that they could explain it was by saying that at late times, there was actually acceleration of the universe rather than deceleration. And when did this acceleration of the universe start? It started roughly about 6 billion years ago. And since that time, by these observations, the expansion, or the decelerating expansion, has been supported by various other investigations, that is the cosmic microwave background radiation, the large-scale structure of the universe, what are known as baryon acoustic oscillations, and weak lensing. Again, I won't go into all these details because of time. And again, for this discovery, these two groups, one was led by Perlmutter and the other one led by Rees and Schmidt, were awarded the Nobel Prize in 2011. Now, how do you explain the accelerating universe? Well, the most widely accepted explanation is the existence of some new form of matter, which is called dark energy. And this is a very exotic type of matter. It actually has negative pressure. And it is believed that this dark energy actually makes up 70% of all the matter in the universe. Now, here is a diagram of a galaxy, and you can see here another bright spot which is circled. And this bright spot actually is the supernova. It's got this, it's named here SN2108, and it's in the galaxy NGC 2525. And this was taken by the famous Hubble Space Telescope, which took pictures of these stars and so forth, which are very far away. Right, so what does the diagram now of the radius of the universe look like if you take into account the late time acceleration of the universe? Now, in this diagram, we haven't shown inflation, but we're more interested in showing the late time acceleration of the universe. So here's your diagram here of the radius. It increases, then there's deceleration here. And finally, roughly at about, say, 6 billion years ago, the universe started accelerating. And roughly this is the present time. And don't worry about these two curves. They are drawn for a zero cosmological constant. This curve is with a positive cosmological constant. This diagram is drawn for k equals +1, but you get a similar diagram for k equals 0, which is believed to be the state of the present universe. It's believed that the current universe has zero curvature, it's flat. Right, so here is a pie chart showing all the matter in the universe. Now, as you can see, the ordinary matter, what is called baryonic matter, which is like your stars, your galaxies, and so forth, which we actually see, like with our telescopes and so forth, that only forms 5% of the matter in the universe. There's your dark energy, which forms about 70%. And then here, there is something which is called dark matter, which is about 27% of the matter in the universe. So you see that most of the matter in the universe, roughly about 95%, is actually in the form of what is called dark matter and dark energy, which we don't detect directly with our electromagnetic radiation. But there are other ways in which you can deduce this matter. So what is dark matter? Well, dark matter, which makes up about 27%, is non-baryonic matter. So it's not the protons, electrons, neutrons, etc. As I said, it does not interact with electromagnetic radiation, and therefore it is very difficult to detect. How do we infer the existence of this dark matter? Well, it is detected by gravitational effects, for example, relating to the formation and the movement of galaxies and gravitational lensing. If you look at the rotation of certain galaxies, what you find is that they are rotating too fast for the amount of matter that we can see with our telescopes. So that means there's more matter there in the galaxy, but we cannot simply see it. Now, what can be the nature of this dark matter? The truth is that we don't actually know at present. Dark matter may be made up of elementary particles which still have to be discovered. That's what most scientists believe in. And there are many experiments which have been carried out to actually try to find out what are these elementary particles which make up dark matter, and it could actually be some new type of elementary particle. But as yet, we don't know what is dark matter. But this is a way in which science progresses. You have something and you try to explain it as best you can. Sometimes you have to bring in new physics or new concepts in order to explain what you see. Right. Now, I want to say a few words about the future of the universe. Sorry, can I just ask how long I have left?
So you have around 10-15 minutes with you, sir.
Right.
So
okay, sure. That's enough to complete
yes.
my talk. So I want to say something about the future of the universe. We mentioned the past, where we have a Big Bang, where everything tends to diverge. It is a singularity, which we still are trying to study. We don't know too much about that. But the future of the universe, well, there was a very interesting talk which was given by Ashok Sen, which I think some of you may have heard of. He is presently at ICTS in Bangalore. Previously, he was at the Mehta Research Institute, which is now called the Harish Chandra Research Institute in Allahabad. And I had the pleasure of actually meeting him when I was there as a visitor in 1999 for about 6 months. He is a very highly regarded, his main area of research is in string theory, and he's won many awards, including the biggest physics prize, which is called the Fundamental Physics Prize, and that's worth about $3 million. Now, when we're looking at the future of the universe, we're assuming that general relativity is valid. There are many other theories which have different kinds of implications, but as I said, there's no time to go through all that. And again, I'll just mention very briefly what quantum theory predicts. And then we'll consider the simplest accelerating solution, where we mention that the radius, goes as an exponential function of time. This acceleration continues indefinitely into the future. So what this means is, if you do some calculations, excuse me, you find that the size of the universe actually doubles every 12 billion years, right? And remember, 1 billion is 10 to the 9. So this is about 10 to the 10 years. Now, what this means is that since it's doubling, it's impossible for us to reach faraway observers due to accelerated expansion. So you see, since the universe is expanding, you've got observers which are moving out of the range that we can actually observe. We're limited by the speed of light. And assuming that we travel at the speed of light, how far will we reach? Well, we can only reach a distance of about 18 billion light years. And this distance is called the horizon. Objects which are further than that are moving so fast that not even light from us can reach them. And they are outside our horizon. As the universe expands, there are more and more objects which go outside our horizon. And in fact, already our observed universe, what we can see, has already split into 15 what are called acausal parts, that is, parts that cannot communicate with each other. So even what is in our present observed universe has already split up into parts that we cannot communicate with. And this has extremely challenging implications. It gives rise to what is called a multiverse, that is multiple universes that cannot communicate with one another. But it's a reality of the prediction of general relativity. Right, what is our nearest galaxy? Our nearest galaxy is the Andromeda galaxy. And we can ask the question, what will happen eventually? Will Andromeda go out of our horizon so we can't see it anymore? Or will it merge with our Milky Way? It will merge with us in about 10 billion years. And what about other galaxies which are outside our local group of galaxies? Well, most of these galaxies will eventually move out of our horizon. And before that, if we could establish civilizations there, if you could get there, of course, then what would happen is, because they are moving out of our horizon, eventually we will lose touch with them, and that would be forever, right? So what about the very, very distant future? Well, our local group of galaxies will be the only ones that will remain within our horizon that we could in principle communicate with. And when the last star in this local group of galaxies dies, then life in the current form will not be possible. In case any of you are worried about this, this is only expected to happen in about 10 to the 13, 10 to the 14 years from now. So at the moment, we are more than safe. Right, and this is actually a very sad and lonely end to our civilization. Now, I just mentioned this is based on general relativity, not taking into account quantum effects. Quantum effects predict that there will actually be a worse end than this, but it is actually more exciting and more adventurous. Now, as I said, we do not have to worry about all this, as the end is very much into the future, and we can let our future go as much as you like. Your generations worry about this. It's only going to occur 10 to the 13, 10 to the 14 years from now. We never know what's going to happen in future. There may be some other more exciting discoveries which would come up, which could change this whole picture. But this is a picture that we have with the current knowledge at our disposal. Right. So conclusion, dark energy and dark matter make up the bulk of matter in the universe. Although there is a lot of research going on in these areas, we still do not know what makes up these dark matter and dark energy. And we can only try to find models of this and see what will happen in future. Maybe in future we will get a better idea and understanding of this. Right. As far as our future is concerned, we can only access a limited region of our universe. With time, the expansion of the universe will convert our universe into a multiple universe. In other words, many universes which cannot communicate with each other. And the rate of this increase in the number of universes is controlled by the expansion rate of the universe. According to quantum theory, what are known as killer bubbles will make some of these universes unfit for human habitation. And there's some function which controls the rate of decrease in the number of livable universes. Now, an excellent reference for the future of the universe, and also some indications of the present universe, dark energy and so forth. This talk, which was given by Ashok Sen, is actually available on YouTube. And this is the link. But if you just Google Ashok Sen, Future of the Universe, you will be able to access this YouTube video. And I encourage those of you who are interested to know more about this to have a look at this. He's got some more numerical calculations in his talk. Right, so with that, I would thank you very much for allowing me the opportunity to deliver this lecture.
Thank you, sir, for such a nice and interesting lecture on dark energy. So I would like to ask participants to raise their hands so that they can ask their queries with the professor. If anyone has any query, then please raise your hand so that we can take up your question.
Seems that everybody has understood everything.
Sir, there are questions in the chat box. There are one or
Oh,
two questions
okay.
in the chat box. So let me just.
Okay, perhaps you could just go through them.
Yes, sir. So one of the participants want to ask whether black hole is part of dark energy or dark matter.
Okay, a black hole is not exactly dark matter or dark energy. What a black hole basically is, if you take a star, even like our sun, what will happen to the star in future? Well, what will happen is that as the nuclear fuel is burnt up, the whole star will collapse down to a very small point. It's like we mentioned about the expansion of the universe, what will happen in the as you go back in time. What would happen to this matter is it will condense to a very small size, again, a singularity where all your quantities tend to diverge. And that basically is a black hole. Now, because a black hole is so strong that not even light can escape from it, there will be a small region which is basically invisible, if you want to call it that, which you cannot see. So you may have heard about the EHT, the Event Horizon Telescope, and that telescope has sort of taken pictures of this black hole, where you see a sort of dark region in the middle, a dark circle, and then around that you see light, which arises from when you study the light, how it goes around the black hole. Then you get that kind of a picture. So it's not dark matter, dark energy. You can sort of more or less see it, except for the dark patch in the center where the black hole is actually not allowing light to escape from there.
So there is one more question that
Yes.
what is the major difference between dark energy and dark matter, or are they both the same?
No. They are different quantities, different concepts. Uh, Dark energy arises when you study, look at stars, etc., which are very far away, and those are moving, or those are dimmer than what you expect. So in order to explain that, we have to postulate that the universe, the expansion of the universe is actually accelerating. And to try to explain that, there is more matter in the universe than we thought of initially, which is called dark matter. So that dark matter causes the current acceleration of the universe at late times. Now, dark matter arises from different investigations. For example, if you look at how a galaxy is rotating, you notice that it's rotating faster than what you expect from calculations. And that means that there's more matter which is present there. And dark matter is thought to be some kind of elementary particle, which still remains to be discovered. But the nature of dark energy is still more or less unknown. It is associated with the cosmological constant, but basically that's all that you can say from a theoretical point of view. So yes, there are different types of matter.
Okay, sir. So, sir, one more question from the participant.
Yes.
So, is there any estimation for the force of dark energy? And what about the density of dark energy? Is it finite or infinite?
No. You see, from the calculations involving the cosmological constant, you can get some idea of like, for example, what is the density and the pressure of dark energy and so forth. And it's not infinite, but of course, we don't know. We can only see up to a certain point, and we don't know really what's actually beyond that. We can just sort of try to infer from our knowledge at present. So it's quite possible that dark energy could be infinite. We actually don't know at present.
Okay.
Despite all the research going on, it's a very active area of research in cosmology today. We still at present do not know the nature of dark energy. Now, let me just say that all which I said in my talk today is based on general relativity.
Yes.
Now, there are other theories where you don't actually need any additional energy or matter in order to get the acceleration of the universe. From the solutions to the equations in those theories, you find that you get a late time accelerating universe. So there are some theories where you don't actually need dark energy.
Okay, sir. So, sir, is there any application of dark energy which you can share with us?
Unfortunately, when it comes to research in general relativity and cosmology, one does not see the direct implication of this immediately. But I just like to add that there's one very practical application, and that is in the GPS. When you try to find in the measurements and so forth that are made, when you want to find a particular location, you actually have to use relativity in order to calculate. Say if you want to go to a certain place, you want to go from, say, Delhi to a certain place in Mumbai, then you put in the address on your garment or whatever, and that will take you to that particular address. But how is that calculation done? In order to do that calculation accurately, you need relativity. Otherwise, what would happen is your distance would be a little off the actual distance. So that's one practical application. But why people are so interested in this is that I'm sure all of us at some point have looked at the sky and wondered, man is always curious about the universe in which he lives in. He wants to try to find out as much as possible about the universe. So that's where the motivation for studies in these areas arises.
Okay, sir. So there are no more questions, sir, in the chat box also. And the chat box is filled with a lot of appreciations. Participants have found your session very informative and very interesting also. So they are really thankful to you for your lecture. So, Dr. Virender, is there any question on YouTube channel?
Hello, Dr. Virendra Tripathi.
Hello. Good morning, sir.
Hello.
It's the afternoon here, but at your place,
it's still morning.
I'm sorry I could not join on time because of examination duty.
That's no problem. If you like, I can send you my slides.
On YouTube chat box, that is dark energy same as dark force or dark matter?
No. I think Dr. Singh actually asked this question.
Yes.
No, it's not the same as dark matter.
They are putting here question only. I think there is no more question. Participants are very happy, in fact, because this is a different lecture they got today in 15 days. So there is no more question. Dr. Rajesh, there is no more question.
Your voice break, Dr. Virender.
Actually, my call is maybe internet issue.
Okay.
I can hear you clearly.
Okay, so must be some issue with my internet, sir. Sorry. Okay, so as there are no more questions and the participants have really liked, sir, your session, they found it very informative and interesting also. So with this note, I would like to thank you for your interesting lecture, for sparing your valuable time for us and giving your lecture here in this refresher course in applicable mathematics and enlightening our participants with your lectures, sir. So thank you once again.
Thank you very much. It has indeed been a pleasure for me to have delivered this talk, and I'm glad that people have found it useful. And again, I'd like to express my appreciation to the organizing team, especially Dr. Virendra Tripathi, for this opportunity. And I hope that your refresher course in applicable mathematics has gone well. I'm sorry I couldn't really attend the other lectures and so forth because of various other commitments that I have at the moment. So I'd like to wish you and the university well in the future.
Thank you, sir. And sir, we will share the links of all the lectures with you. So if you are interested in that, you can definitely watch them. So they are all recorded lectures, so you can watch them, sir.
Yes, thank you. I would be interested.
Okay, sir.
Okay.
So thank you, sir. So for participants, I would like to inform you that the feedback form is live on the portal. So you all can fill the feedback form for the today. Also, there is a Google form for certificate. I think many participants have already filled it. Those who have not filled it, they should surely fill it by today, so that we can continue with the other procedures of certification, so that it might not delay the certification process. And this was the last lecture of this refresher course in applicable mathematics. So we are ending our refresher course here. It was a very good refresher course, and many participants have conveyed their best wishes and also found it very useful for them. So once again, thank you, everyone. So with this, I am ending this meeting. So if there is any participant who want to ask anything, they can ask, else I am ending this meeting now. And one more thing, the certification process might take 15 days. So please bear with us. We will be happy to deliver the certificates as soon as possible, but we might take some time. So please bear with us. So thank you, everyone. Now I'm ending this meeting. So there are no more quizzes for this session. So we are officially ending our refresher course here. And yes, so we are ending our refresher course here. Thank you.
Okay, bye, everyone.
Bye, sir.
Bye, sir. Thank you so much, sir.
Thank you, though. Thank you. Okay, one of the participants want to ask